Bismillahirrahmanirrahim. Assalamu alaikum students. In our previous lectures, we have discussed the concepts of differential forms, the exterior derivative, the p cubes, and the p minus faces of those p cubes. Now we continued our discussion with the integration because we want to perform the integration on the manifolds. So first we briefly revise the integration on Euclidean space because we are familiar with the concept of integration. We have studied this concept in our real analysis course in the form of the Riemann integration. So the standard measure of a rectilinear P cube, so this is a P cube, is to be P mu Pu. So we associate a real number with this P cube in the form of a measure, and this will be equal to B1 minus A1 into B2 minus A2 into BP minus AP. So mu P basically is a mapping that assigns numbers to these cubical subsets of RP. For example, if you see that for a one cube that is defined on R, we define mu Pu to be mu1u, and in this case it will be B1 minus A1, and this is nothing, this is the length of the interval. On R2 we have mu2 of u, which is equal to b1 minus a1 into b2 minus a2. So the measure of the 2 cube is basically, it's nothing, it's the area of a rectangle. On R cube, you can see that mu3 of u, which is the measure of the 3 cube, will be b1 minus a1, b2 minus a2 into b3 minus a3, which is basically the volume of a 3 cube. So it basically, this measure associates numbers with these p cubes. So in the 3D space, we are familiar with the length, area, and volume. So we have linked it with the ones we have already know. So the Riemann integral of a real valued function is f defined on the cube u, if it exists, is given by f d mu p. So we integrate the function f on with the differential of the measure d mu p over the cube u, then this will be basically limit uj tends to 0, and we have basically divided this cube into n subcubes. F of xj mu p uj. We explain this through this figure shortly, where u has been broken up into smaller p cubes uj, and a point xj has been chosen in each uj. Consider f on R, then u is a closed interval a1 b1. Since u is a 1 cube, so it will be represented by a closed interval a1 b1 on R. So we have shown this closed interval over here. Then we have divided this interval into sub-intervals. You can see we have divided it into a1 a2, which is represented by u1, a2 a3 represented by u2, a3 a4 represented by u3, a4 a5 represented by u4, a5 a6 represented by u5, and a6 b1 represented by u6. So this 1 cube is converted into 6 small 1 cubes, and we have taken a point x1 in u1, x2 in u2, and so on, x6 in u6. Now we find the value of the given function on this point x1, x2, and up to so on fx, and we multiply this value of the function with the length of this subinterval. In this case, you can see that it is a2 minus a1, here it is a3 minus a2, here it is a4 minus a3, and so on. So we multiply this length with the height, and we get basically the area under the curve, and we sum up this. And if we take this limit to be 0, this limit to be 0 means we want to make this interval as small as possible. So if we refine this, we have divided in first step into 6 subintervals. If we divide into 12, 100, 200 intervals, then this length of the interval will be very small, and we can move towards the actual area under the curve, and this way this will approach to this value of this integral. And this is the famous Riemann integration you have done in your real analysis course. So in this case, you can see that f d mu1 from a1 to b1 will be f of x1, the value of the function at this point, into the length of this interval, plus the value of the function at point x2 into the length of this interval, and so on. So we can say that this mu1 uj is basically uj plus 1 minus uj is basically the length of the sub interval. So in this way, we can calculate the integration on a function of one variable defined on a one cube. Similarly, for a function of two variables in R2, the rectilinear 2 cube is a rectangle between A1 and B1 along x-axis and A2 and B2 along y-axis. You can see we have shown this rectangle over here, and then the integral will be f d mu 2 will be limit uj tends to 0. We have sum up all these and is equal to f of xj mu 2 uj, where this is the value of the function which lies in a sub cube, and this is the area of each uj, and this means we have to make it as small as possible. So in this way, you can see that we have divided into 24 sub rectangles, and u1 up to so on u24, and we have taken one point in each of these rectangles, say x1, x2, so on x24, and we find the value of all these points, multiply these values with the area of the respective two cube, and when we sum up them, we get the area under this volume under the surface, and this will be represented by the integration of this aspect. So here you can understand that once again we have used the concept of Riemann integration to integrate a function of two variables, and similarly we can use this concept to find the integration of a function of p variables. There is a statement of an important theorem known as the Fubini's theorem. If f is continuous on u, then the definite integrals fp u1 u2 up to up minus 1 is equal to the integration of the function dup from ap to bp point. This is very simple, that if you have a function of three variables, suppose you have a function f of x, y, z, and you integrate it with the variable z with the definite integral values, say a3 to b3, then the answer will be a function of two variables, because you have integrated in the value z and you have substituted the points for z, so the function is left with the two variables x and y. So if you have to integrate the function of p variables with one of the variables, the answer will be a function of p minus one variable. These are continuous function of the parameters u1, u2 up to up minus 1, and Riemann integral of f is given by, then you can say that if we integrate this function on the p cube is same as integrating this function on p minus 1 cube. So if we integrate f on the p cube, this is equivalent to integrating this function on the p minus 1 cube. So if we continue this process, then you can see that for a iteration process, we can see that we can find the integration by integrating step by step with the all available values of the parameters. For explaining this, you consider this example. This will explain you that what we have stated in Fubini's theorem, that consider p is equal to 3, then f is a function of three variables, say u1, u2, and u3. Now, if we want to integrate this f with respect to the variable u3 from a3 to b3, then the answer will be a function, say f3, which depends on two variables u1 and u2. And if the Fubini's theorem says that integrating f on a 3 cube is same as integrating this f3 on a 2 cube. The result is always the same. Similarly, if we continue this process, we can integrate f3 on a u2 cube, and this will be given by f2 d mu 1, because again, if we integrate this with the variable u2, the answer will be a function of variable u1, and by the same procedure we get these two integrals to be equal, where f2 u1 is the nothing, it's the integration of function f3 with respect to the variable u2. And thus, if we continue this process, we can first write this, and the answer is this one. Then we integrate this and we get this, the answer is this one. And then we integrate this one with the variable 1, and we get the answer with the integration from a1 to b1. So this example explains that we can integrate step by step with the variables 3, 2, and 1 to find the actual value of the integral. Another important thing is that we can usually use the change in variable theorem for the Riemann integrals. Suppose we have two regions E and D, and those two regions are connected by a mapping phi that maps the points from E into D is a C1 bijective map, and this is a continuous map. And the integral I, which is the integration of the function on the region D, exists. Then we say that if we transform, we operate f of phi, then this f of phi means we have transformed the region from D to E. Then the integration of f of phi E and the mu p, which is basically the volume element, or you can see that the Meyer, then this Meyer will be transformed in new coordinates with the determinant of the Jacobian exists. Then we say that the integration of this function is same as the integration of this function. So we can either integrate the function in the domain D, or we can integrate the function in the domain E. In both cases, the answer will be the same. We explain this with an example. Suppose D is the region x, y, A is less or equal to x is less or equal to b, and h of x is less or equal to y is less or equal to k of x, where h and k are c in one functions, means they are continuous functions. And from here it is clear that h of x is always less or equal to k of x for the points A is less or equal to x is less or equal to b. Consider another region E uv such that a is less or equal to u is less or equal to b, and 0 is less or equal to b less or equal to 1, and we can define a mapping phi from E to D such that x is equal to u and y is equal to vk plus 1 minus vh. So from here you can see that whenever you put u is equal to a, you get x is equal to a. When you put u is equal to b, you get x is equal to b. When you put v is equal to 0, you get h of u, and when you put v is equal to 1, you get k of u. So between 0 and 1, you have the values between h of x and k of x. So this mapping transforms the points from E to D. And we have shown this in figure, that this is the region E, which is in the form of a rectangle, and this is the region D, which is in the form of these functions, and this is the function h of x, and this is the function k of x. From here you can see that x is equal to a and u is equal to a are the same lines, x is equal to b and u is equal to b are the same lines. So the mapping between u and x is the identity map, which is u is equal to x. But v is equal to 0, which is a line over here, is transformed to a function h of x, and v is equal to 1, which is a line over here, is transformed to a function k of x over here. So we need the Jacobian of the transformation. So for the Jacobian of the transformation, we determine partial x by partial u, partial x by partial v, partial y by partial u, partial y by partial v, this matrix. We substitute the values of these derivatives over here, and we find the determinant 2 of k minus h, which is always positive. Then the integral this one is equal to this one, and if we put the change of variable like this, then we can convert this integral to be this one. So when v is equal to 0, y is equal to h, when v is equal to 1, y is equal to k, and if we substitute this over here, this integral will be equal to f of x by dy dx. So if we use the integration over this integration become easier. So which is the standard form of Fibonacci's theorem, because we have converted this integration into two integrations by two different coordinates. Now, for example, consider f of xy to be xy, h is equal to x, and k is equal to x square. Then you can see that the integration of f of xy d mu over du must be equal to a to b x to x square x by dy dx. So we perform the integration with the variable y. It will be in this term, and then we perform the integration with respect to the variable x, and we get this answer. So in this way, we have performed the integration on the Euclidean space by the change of the domain and by using the Fibonacci's theorem. This is enough for this lecture. Thank you very much for your attention. Thank you.